Good morning, Astronomy 1010. Welcome to our 12th lecture. I hope you all had a great Thanksgiving. We are getting close to the end of the semester here. I think just a couple of weeks left to go, right? So this is the home stretch, something to think about. Today, we're going to do a lecture which kind of finishes planetary atmospheres, but it's also aiming to do something else, which is to sort of wrap up and summarize all of the things that we've learned about terrestrial planets so that we've got a good handle on how terrestrial planets evolve over time. And once we have that, we're going to cross the asteroid belt. And by next class, we'll start moving into the Jovian worlds. Today's lab is going to be a classic astronomy lab on building a basic Keplerian style refracting telescope. It's short, it's easy, it's fun. On Wednesday, the homework session we're going to do is going to be on planetary atmospheres. So we didn't do one last week. Last week we talked about planetary atmospheres. Today's lecture is part planetary atmosphere, but it's also part summarizing and understanding the big picture about terrestrial planets. And I figured I'd start today with some notes on that. While you guys are fresh and you're still listening to me, maybe we could talk about one of the most important messages that I have for you today. Hold on, I just saw this thing, worksheet lab 9. Oh, that's because it's lab 9 in the lab book. Remember the books, Hava, that nobody bought and nobody read?
I bought them.
Oh, cool. Awesome, Andrew. You were awesome. Did you read them?
I have both of them. I haven't read them.
In the Wilson Astronomy Lab Manual, it's lab number 9. But
I bought a book too.
It's our internal auditing lab 7. Does that? Okay, she understands now. All right, so sorry. Let me get it back to me here. Get to my Blackboard. Okay, so what do we want to talk about today? I wanted to start today with probably what's one of the biggest takeaways of this course, which is what causes a planet to change or evolve over time. Earth 4.6 billion years ago did not look the same as Earth does today. Do you guys remember what Earth would look like if you could go back to its formation? What would Earth be like if you went back 4.6 billion years ago? What are some ways it would be different from our own planet today?
It probably wouldn't have as many like mountains and like valleys.
So mountains and valleys are caused by plate tectonics. And without water, there might not. I mean, I was thinking of some more basic things, Jake. I was thinking, first of all, it wouldn't have an atmosphere. Or if it did have an atmosphere, it would not be oxygen and nitrogen. It would be some weird trace gases, maybe even some helium stuck to it that was slowly bleeding away. Remember, Earth forms from a protosolar nebula, which is hydrogen and helium and little bits of dirt and metal, right? So it might have volcanoes because it would have it might even have a molten surface, Jake. You know what I mean? So I guess maybe it wouldn't have, maybe you're not wrong. Maybe it wouldn't have mountains and valleys. But I would think there were some bigger things. First of all, like it might not even have an atmosphere. You know, the atmosphere has come from volcanic outgassing. Planets change and evolve over time. One thing I thought about doing today, I don't have this in my slideshow, but I thought today about looking at a plot of Earth's oxygen as a function of time. So if I typed in Earth's oxygen history, I've seen this graph before, and it's pretty wild and crazy if you look at the gyrations that Earth goes through. No, I don't want this. Let's just look for the image for a plot. Yeah. This is a plot of the amount of oxygen in Earth's atmosphere over the last billion years, right? Let's think about this. By the way, what percent are we at today again, class? What percentage of Earth's atmosphere is made of oxygen? That's a test question.
20.
21%.
Oh,
Whatever. Fine.
so
You're close. Look at this blue line. This goes back 1 gigayear, 1 billion years. So this isn't even the whole history of Earth because there wasn't any oxygen when it first. Look at this. There's a rise of oxygen, a huge buildup, then a decrease. Look at that. Planets evolve over time. Earth has not looked the way it looks today for its entire history. Planets change. The changing of their atmospheres and their temperature would be called climate. But the changing of the planet itself, mountains and valleys and continents, those are part of its geological history, right? What causes planets to evolve over time? It turns out to be some basic things that have to do with physics. Let's take some notes on this. We like to call these the 3 fundamental planetary properties. Now, the first thing I want to mention before I talk about the 3 fundamental planetary properties is we're just analyzing planets within our own solar system. And if we analyze terrestrial only for a second, then one of the things that you would think was the most basic, which is chemical composition, is not one of the 3 fundamental planetary properties. And that's because while there may be differences between Jovians and terrestrials in terms of chemical composition, within the terrestrial zone itself, all terrestrials are made of the same thing. And what would you guys say terrestrial planets are made out of? If a terrestrial planet was a cocktail, what ingredients would go into it?
hydrogen.
False. Completely false. There's
Or no. What do you mean by that? Is it elements?
I mean that you like stuff like a martini is made from vodka and vermouth or something, right? So
All right.
what are the ingredients that make up a terrestrial planet?
Would one of them be metal?
Metal is one of them. And what's the other one?
Rock.
Yeah, rocks and metals. That's why chemical composition is not a fundamental planetary property. So I almost didn't want to write that down, but that's worth thinking about if you hadn't thought this thought before, okay? What are the 3 fundamental planetary properties? In the terrestrial zone, the first is size. Size affects planets in a number of important ways. First and foremost, the amount of gravity that the planet has. Secondly, we've learned that the size of a planet, its physical radius, is related to its amount of internal heat. Why does internal heat matter for the evolution of a planet? What does internal heat have to do with what we've been discussing over the last few chapters? Do you guys remember anything about the internal heat of planets? Maybe you need a slide to jog your memory here. Wait, not that one. '21. How does the internal heat affect a planet? How do we measure the internal heat of planets? Which of these planets have internal heat and which do not? I'm going to ask you a series of simpler and simpler
Earth
questions.
and Venus.
Okay, fine. Earth and Venus, Jake, thank you. And how did you know Earth and Venus have a lot of internal heat?
Because the lithosphere is thinner.
Thank you. This man's talking sense to me. And what aspect of a planet's features does the internal heat determine? Planets with more internal heat tend to have what on their surfaces?
Volcanoes?
Yeah, volcanoes for one. Maybe an atmosphere. Maybe some plate tectonics if there's water. Maybe water. Cool stuff. Stuff that's fun to play on if you're an alien, all right? It's not fun to play on Mercury. It's not fun to play on the moon. Well, maybe it's a little fun to play on the moon. I don't want to get too crazy here. Okay, fine. So the internal heat will, in its own way, determine the amount of geology that you have, right? Gravity will help you hold on to an atmosphere. Okay, what's the second thing? The second thing is your distance from the sun. What property of a planet does the distance from the sun affect? I don't want to say determine, I want to say affect.
The external temperature.
Very good, Jake. Jake, you have a career in planetary science waiting for you. The surface temperature of the planet. Which has lots of implications for everything from liquid water to, well, what the planet's made out of if you think about the frost line. Three is the most surprising. It's the rotation rate. And I hope to convince you of that as part of our lectures today. The rotation rate does one or two things that are really important for the planet. The first is I'd like to remind you guys that we require a rotation rate for a planet to have a magnetic field. And up to now, the magnetic field from your point of view is mostly a curiosity. On the other hand, it turns out that the magnetic field plays a huge role in protecting planetary atmospheres from harassment from the solar wind. The other thing that we have to talk about today as part of our lectures is rotation rates affect atmospheric circulation. Atmospheric circulation is deeply tied into wind erosion, but it's also tied into Earth's water cycle in a way. And those things can have a very positive benefit on a planet. I hope to justify these things today. Okay, guys, I want to take a 2-minute pause here. Give me a moment if you can, and I'll be right back. Sorry about that, guys. Here we are. Does everyone have these notes down? Because these are pretty important things for the big picture of our class. I think on the exam, which will come up in a couple of weeks, a lot of questions that you're going to have to deal with are going to be kind of based on these 3 fundamental properties. So I started the lecture off today with these things for a reason. This is a big picture concept. The 3 fundamental planetary properties, they affect the amount of geological activity that a planet is going to have on its surface. Today, I want to talk about the histories of the planets, but I also want to talk about some things that Earth does uniquely because of its atmosphere and its rotation. Earth has just like the perfect mixture of these things to support life. It's large, so it has a lot of internal heat and active geology. It has not too hot, not too cold surface temperature. It has a healthy rotation rate with atmospheric circulation and a magnetic field. All of those things are responsible for you being here today on planet Earth to listen to this lecture. Okay? So how do I want to tackle this? I suppose we should start with some things about Earth first, I guess. All right. So let's return to our atmosphere lecture for a moment. And let's think about some of the things that make Earth unique in terms of atmospheric circulation and geology. In our, oh, excuse me. Let's find the atmospheres lecture. Here we go. In our last lecture, you guys learned some very technical things. You learned about the no greenhouse temperature, how hot a planet is, and you also learned about thermal escape. So let's just ask a couple of simple questions to see if you remember some things. Oops, I want to go back here. Let me drag you guys over to the side this time. Here we go. So class, what layer of our atmosphere does thermal escape take place in?
The exosphere?
Thank you, Jake. Why can't thermal, first of all, how would you describe thermal escape? What is that? It's something that happens to atmospheres. No fancy words, just
Kind of like the heat radiating off the planet.
I'd be careful about that because radiation is electromagnetic. Thermal escape is about gas particles. Anybody else besides Jake know anything about astronomy? Whoop.
Is it the gas particles that leak into space?
Yeah, that's a simple way to put it. Just the leakage of gas particles into space. And if they travel faster than the escape velocity, some of them are always going to be sort of bopping off the planet. That can only happen in the exosphere, Jake, because in the lower levels, the gas particles are too dense. Even if the particles are moving very fast, they're going to crash into their neighbors. They can't get a free path out into outer space. Up here, the particle density is really low, so low, in fact, that you guys would just think you were in the vacuum of space. When the particle density is really low, those particles which travel wicked fast, to say something very Rhode Island, they would be able to achieve thermal escape by traveling above the escape velocity. Thermal escape is important. All atmospheres do it, but Earth, of course, has these volcanoes that are active, and the leakage of gas is very slow, and the replenishment from volcanism is high. So Earth doesn't really lose its atmosphere over time. Neither does Venus. Mars's atmosphere seems to be thinning out over time. And of course, Mercury and the moon barely, they never even had one to begin with, right? We also talked about what makes the real surface temperature of a planet hot. Oh, hey there. It's nice to see some other friends joining us for a change. Michael, nice to see you. What's the hottest planet in the solar system? Who knows?
What's the hottest one in the solar system?
The hottest surface temperature of any planet in the solar system. Which planet has the hottest surface temperature?
Venus.
That's right. It's not the closest planet to the sun. It's the second closest planet to the sun. Why is Venus warmer than Mercury at its surface?
As an atmosphere?
Yeah. And last time, just to remind you what we did in case someone missed the show, we learned that atmospheres are affected by a few different things. They're affected, of course, by your distance from the sun, but they're also affected by the global albedo, the amount that it reflects light versus absorbing light. Concrete, asphalt, blacktop, these things absorb photons and they become hot and re-radiate. Things like fresh snow or ice, they tend to reflect a lot of light, and therefore the light is not absorbed and it does not heat up the planet. Lastly, if a planet has an atmosphere, key gases called greenhouse gases, which make just a very small percentage of the total concentration of the atmosphere, those greenhouse gases are wicked good at absorbing infrared photons from the surface, and they heat up the atmosphere of a planet. So the amount of greenhouse gas that a planet has will play a huge role in determining its temperature. This is why Venus is hotter than Mercury. Mercury has no atmosphere. It's just a rock sitting in sunlight. So of course on Mercury, if you're on the so-called sub-solar side here, your planetary rock, when we talk about the temperature of Mercury, we're talking about the rock temperature, is extremely high, maybe, 400 degrees Celsius or something. The backside is -1, 200 Celsius. It's 100 Kelvin above absolute zero, right? You can't really have a uniform temperature because there's no atmosphere. It's either you're in the sun and some people suspect, by the way, that there could be craters along the north or south pole of Mercury that are always sitting here at the terminator. And at the terminator, it might be just right where you're kind of in shadow all the time. And there could be some primordial ice left over from the early solar system. No one's actually found this stuff yet, but the Mercury Messenger spacecraft certainly spent a lot of time peeking into craters, looking for any primordial ice that could be sitting there. Astronomers, planetary scientists would love to get their hands on some primordial ice. They want to taste the protosolar nebula. They want to know what was the exact composition of water in the early solar system, and how might that differ from the water molecules in our ocean today? They could compare their amount of deuterium to learn about their history. Anyways, planets with atmospheres can potentially have a greenhouse effect. And you guys remember what greenhouse gases are, right? What are some examples of greenhouse gases?
Greenhouse gases.
CO2.
Oh,
CO2?
methane.
Methane, one more.
HO2, water.
Or H2O, right?
H2O. That's what it's called.
Water's a greenhouse gas. What percentage of our atmospheric gas does water make up? Tasty water. What percentage of our atmosphere does it make up? Anyone remember?
0.4%.
Yeah, like 0.5%. How about CO2, Noah?
0.04%.
Yeah, 0.04%. And why am I reminding the class about that, Noah? Because I want to show you a picture from your book that nobody reads. It's a picture of how the surface temperatures of the planets are today versus what they would be without their greenhouse gases. Now, follow along with me on this, class, okay? This is in Celsius. Mercury has two different temperatures, 400 degrees Celsius during the day, -200 degrees Celsius at night. So I was pretty close. Venus has a temperature of 470 degrees Celsius. That's definitely hot enough to melt lead. According to this, the temperature of Venus, well, actually, let's start by looking at Earth. Okay, let's go to blue for Earth. The average temperature, if you average the poles and the equator of Earth, is 15 degrees Celsius. And that's probably like 65 degrees Fahrenheit. Let's just fact check that here. 15 Celsius to Fahrenheit. Okay, 59 degrees Fahrenheit, excuse me. So the average temperature of Earth is about 60 degrees Fahrenheit. In the absence of the greenhouse effect, in the absence of that 0.4% that Noah just mentioned of water and 0.04 of CO2, the average temperature of Earth would instead be -15 degrees Celsius. Would you guys like to live in a world whose average temperature was -15 degrees Celsius? Would that be helpful for living organisms? Not. I mean, life might be able to survive there, but it would be a lot less fun for us, right? No more trips to the beach if the average temperature, well, at least not in Rhode Island. That would definitely, over time, probably increase the size of our ice caps, and it wouldn't be helpful for living organisms, that's for sure. Not for living organisms like us, anyways. But it's still within the habitable zone in a way. You know, you could live on Hoth, for instance, okay? Venus is a bit weirder. The average temperature on Venus is oh, by the way, I would like to point out that is a net temperature change. This last column here is delta T, your change in temperature. On Earth, you get a net difference of 30, and they actually screwed this up. When you do temperature differentials, you're supposed to put the degree symbol there. 32 Celsius degrees of temperature change, which is pretty freaking profound if you think about it, right? Celsius is double that of Fahrenheit. So that's close to like 64 degree Fahrenheit degree change in temperature, which any of us would consider profound, right? On Venus, it claims that without the greenhouse effect, the average surface temperature would be minus 40 degrees Celsius. WTF is that all about? Wouldn't you guys expect that Venus would be hotter than Earth since it's closer to the sun? They're claiming that in the absence of the greenhouse effect, Venus would be colder. Do you see why they're doing that? Look at that chart there. What's going on? They're using a global albedo of 72% from the cloud tops, which is ridiculous because they're calling it the no greenhouse temperature, but they're still using the albedo of the greenhouse gas cloud tops. Do you guys remember what color the surface of Venus is?
Is it like yellow?
That's the cloud tops. That's the 72%. What about
Oh,
the
yeah, yeah.
surface from those two pictures? Come on, let's go to our planet. Remember I showed you guys the pictures of Venus? Didn't I do that? What did it
White
look
is-
like? What did the surface of Venus look like? Anyone? Sorry, I'm looking. Oh, there we go. It looked like this. Right? So, what color is the surface of Venus?
I don't know, like reddish brown.
I think you have to think, you're looking through this like yellow hazy atmosphere. I think that looks like black volcanic rock to me, Jake. I think I don't have a sample of Venus rock here to show you, but I think that would be very dark black volcanic rock. Because look at the washed out color of the spacecraft
Yeah.
here, right? In fact, I suspect they might have taken this as a black and white image at infrared wavelengths. I believe that the atmosphere of Venus is so opaque to visible light. I'm not sure, Jake, that we'd be able to see our hand if it was like out in front of us because the
Wow.
gas is so thick. So they might have had to use longer wavelength infrared light and take a grayscale image and then kind of false color it. That's why it kind of looks like those tin type daguerreotypes from the Sherlock Holmes era. You know what I mean?
Yeah, it looks like sepia.
Yeah, sepia tone or whatever you want to call it. So I think that's what we're looking at there, Jake, is black volcanic rock. The point that I'm trying to make, and I guess I'm being a little long-winded about it, is without the greenhouse effect, Venus would not be negative 40 degrees Celsius. Your book did a disservice to you there. I don't know what the actual number would be, but well, we could calculate. Hey, I've got a great idea. Let's do a sample calculation. We have the power to figure out what temperature would Venus be if, and I don't know the answer to this, so this is going to be fun for me for once, okay? Here's a question that I could ask on the final exam. Question. How hot would Venus's surface be in the absence of an atmosphere? I was just thinking we don't know what that is, and then I realized we have the power to calculate it. The distance that Venus lies from the sun is 0.723 astronomical units. And now we need a value for Venus's global albedo. What do you think we should choose as a representative albedo for Venus's surface? And here's a couple of other albedos to get your mind stimulated there. Noah, what do you think? What would be probably the best of all these albedos to choose?
Maybe like concrete.
Or maybe even like another astronomical body that's covered in
Oh,
volcanic.
the moon?
Right, because isn't the moon also covered in jet black volcanic rock?
Yeah.
I'd say that's probably your best bet. This is what the book should have done, but they failed, so we have to clean up their mess, okay? So what would you give me for a number then, Noah?
7%.
7%, yeah. So that's 0.07. Okay, and we're going to use the no greenhouse temperature, right? Which tells us that the temperature of the surface of a planet is 280 Kelvin times the fourth root of 1 minus the albedo divided by the distance squared. Let's go ahead and plug in our numbers, okay? 280 Kelvin. One minus 0.07 divided by 0.723. Normally I would put AU, but Noah and I had this I think Noah and I had this conversation about the unit thing last time, right? You remember, Noah, that they hid all the units in here so that it comes out in Kelvin. Okay, last time, oh, by the way, this is not the square root, this is the fourth root. Last time I taught you how to punch this into your calculator. Let's see who remembers how to do it. And Yin, I like seeing you here today. I want to see you doing the punching. We lost Michael, but I wanted to see Michael doing some punching too. I want to see everybody punching. Punch them up. I'm going to punch mine up. Well, who's got a number for me? Jake, what do you got?
I was just gonna ask for some help because I missed last class, so I'm not like fully
Ah.
with this yet.
Oh, I see. I see. Well, okay. Here's our strategy, Jake. We're going to do 1 minus 0.07, and then we're going to hit equals. Then we're going to divide by 0.723 squared, and then we're going to hit equals. Then we take the fourth root, and then we back multiply by 280. Hold on, I might need to turn my lights up here. Usually I can just kind of hold this up and, all right, there. Oop. I kind of have to angle this today. I don't know what's going on. Okay, ready? So we'll do 1 minus 0.07 equals, there's 0.93, divide by 0.723, square thereof, then we equals it. Now we're going to take a fourth root, shift arbitrary root 4 equals, and now we back multiply by 280. What'd you get? Do it. Okay, Matt, read it out to us.
323.4.
Well,
How many?
why
sig
not?
figs?
Why not 0.37736664? Why just stop there? Why not give it to me to 10 decimal places? Or maybe, Matt, instead you should, round it off a little more. Round it to 2 sig figs, buddy. How do we round it to 2 sig figs?
320.
Yeah, 320 Kelvin. Do you guys know how to convert that to Celsius? If you subtract 273, I'm not feeling smart enough to do that in my head today.
47?
Yeah. Is that a nice place to live? Well, first of all, there's no atmosphere, so it's not a nice place to live. What's 47 degrees? What'd that be in Fahrenheit, huh? I gotta
Over
cheat.
100.
Yeah, that would suck, right? Whoa, I got it right here. Yeah, good class. So Venus should be quite warm. Jake, do you have a question or?
Yeah. I just missed it when you were doing it, but which one is the arbitrary root button?
Right. So it's, let me tell you some stuff from math, Jake, to help you remember. The fourth root, what that really means, the fourth root of x, it really means raise x to the power of 1/4. Those are two different ways of saying the same thing, okay?
Oh,
So rather than put a fourth root symbol, for some reason, your calculator chose instead, where is it? The x to the 1/y button, which is the yellow second function version of the x to the y. So
okay.
you've got to hit the fourth power. For instance, 2 to the power of 4 is 16. But if you want to take the fourth root of 16, you go shift arbitrary root 4 equals. So
Okay.
it's the shift and then x to the y.
And then whatever. Yeah. Thank you.
My point is, what's the composition of Venus's atmosphere? What is Venus's atmosphere made out of? That's a test question. I'm going to ask that to you. So you might as well learn it now. Look in your notes. What's the composition of Venus's atmosphere?
CO2, nitrogen.
But give me some
I think that's
percentages,
it.
Noah.
It's 96% carbon dioxide and it's
All right, stop.
3.5%.
I'm bored after that. 96% CO2. That's what basically Venus's atmosphere is, a big old pile of CO2, right, Noah? And that's why its net change in the greenhouse effect is a change in 500 Celsius degrees, which is crazy, right? Hey, Noah, what's the composition of Mars's atmosphere?
Same thing, pretty much.
Yeah, it's also 96% CO2. Noah, I got a thought question for you. On Venus, we went from, well, what should have been 40 degrees Celsius. It should have a positive there. And we had a net change of 500 Celsius degrees. Mars has an actual average surface temperature of negative 50 degrees Celsius. Whoosh, that's cold. But without the greenhouse effect, it would be negative 55, meaning Mars only gets a temperature differential of 5 Celsius degrees. My thought question is, Noah, why would Venus, who's made of 96% greenhouse gas, have such a dramatic change in temperature? Mars is also made of 96% greenhouse gas, but it only changes by 5%. Why is it different on Mars?
The concentration of those gases is probably way different. Like they have the same percentage, but there's probably a lot more carbon dioxide in Venus's atmosphere.
Excellent, sir. You do me proud. That's right. I mean, I was talking to one of the nighttime students last night because they were telling me a cool story. I think that was James Quinn was telling me this cool story about how he worked in a chemistry lab, and they had a vacuum where they would boil water. They would test the boiling point of water inside of a vacuum, and water was boiling inside their laboratory at 80 degrees Fahrenheit, not 212, but 80 degrees Fahrenheit because of the pressure of their vacuum. Now, I didn't find out what the pressure of his vacuum was. He may not remember, but it got me thinking, what's the pressure of the do you know what the pressure of Earth's atmosphere is in kilopascals? What's Earth's atmosphere?
14.7.
Well, that's in pounds per square inch, but all right. There's so many different pressure units. Hold on. Atmospheric pressure. I think if you want to do it in pounds per square inch, so they have this in 6 millibars. So 14.7 psi is Earth's atmospheric pressure. Mars's atmospheric pressure is 0.095 psi. If you divide this number by that number, you get a factor of 150. So Mars's atmospheric pressure is 150 times less than Earth's. I'd like to see it in kilopascals because I'm a metric units guy, right? Atmosphere of Mars. They'd probably have it in kilopascals on the Wikipedia page. I'm kind of doinking around here. Whoops. Yeah, it's less than 1%. It's 1/150th. It would have been nice if they had given it to us in. I'd like to find a way to measure the content of it, and if I goofed around on the internet, I'd probably find it. But it gives you a sense of what we're talking about. If pressure and density are proportional by the ideal gas law, if P is equal to NKT, I like to think of the number density and the pressure as being somewhat proportional to each other. So I'd like to think that maybe the density was also about 150th of Earth's atmosphere. That's quite thin. So Noah had the right idea. And Noah, it should have the same amount of greenhouse effect, but there's just so little gas on Mars that it doesn't really affect it that much. That gets me thinking, Noah, because if we look at the surface of Mars, we see a history that looks pretty wet and wild, right? Do you guys remember that if we looked at that Mars MOLA map, I could call that up. Actually, rather than tax the internet here, I've got the labs and Mars topographical map. Remember that we had a lab where we kind of explored the surface of Mars together. That was kind of fun. And if we poke around here on the surface of Mars, we certainly see a history that was probably different and more atmospheric rich. These, of course, look for all the world like dried up riverbeds. And remember that we have a rover called the Curiosity rover, which is currently exploring Mount Sharp in the Gale crater. And they've basically confirmed by studying the mineralogy of rocks that there was once water inside of Gale crater. So this used to be a pool of water in here and probably in here. And this was probably all liquid water too. You couldn't do that with a pressure of 0.09 pounds per square inch, right? I don't know why the hell I'm using imperial units, but that's all I could get on the internet. So you at 150th of Earth's atmospheric pressure, you can't get liquid water like this. That means Mars probably had a thick atmosphere at one point. It probably had a giant ocean. We even suspect that it's possible it could have developed basic microbial life, right? That's why we spent all this money sending these rovers there to drill into the soil. We just want to find one little creepy crawly on Mars, and then we'll know that life is a natural consequence of the chemistry of the universe. It's not like Jesus waved his magic wand and that's why the dolphins showed up. It's a natural consequence. It's a natural consequence of the chemistry of planets itself, which would be extremely cool. Let's talk a little bit before I burn this whole lecture up. Let's talk about some of the things that make Earth special and some of the unique aspects of Earth's distance and atmosphere. There's some things that I wanted to share with you that I'm afraid I won't get to. So I'm going to kind of bop around here. I want to talk about circulation on Earth, Earth's water cycle. One of the things that it turns out that makes Earth so special, why it's had, so you know what Earth has that Mars didn't have, that Venus didn't have? Earth has had climate stability. And what that means is our temperature has remained roughly constant for like 1 billion years or so. And there's several different factors that have gone into making our climate stable, whereas clearly you can see Mars's climate was not stable. At one point there were volcanoes and there were rivers and there were oceans, and now today it's just an asteroid field, right? It's just a beat up terrain of craters and a little bit of atmospheric gas. Venus, on the other hand, has baked itself dry like a clay pot in an oven. And Venus probably once had a period which was not so hellish. It turns out that the rotation rate of Earth, the combination of magnetic field plus wind erosion, plays a huge role in that. And let me just tell you a couple of interesting things. You guys, of course, most of us are living here in Rhode Island. We've spent most of our lives here. And if you watch the Weather Channel, you'll always notice that wind patterns are migrating from the West Coast to the East Coast. That turns out to be a natural, there are like northerlies and other things, but in general, you see weather storm systems coming across from west to east. There's a reason for the directions of winds. They have these trade winds along the equatorial routes and westerlies and easterlies. These are related to the rotation rate of Earth. And I want to talk to you guys about that. First, let's just talk about atmospheric circulation. I want to talk to you guys about these things called Hadley cells, named after a scientist who first described how they would work. And in this picture that you see here, they show Earth underneath, but they probably should have shown the planet Venus, because this is what circulation looks like on the planet Venus. Let's take some notes on this. This is important. Ooh, almost lost a dude. I lost a bauble. Okay. So I want to spend a few minutes talking to you guys about atmospheric circulation. So there is this concept called the Hadley cell. Hadley cells are basically just big convection cells in a planet's atmosphere. So Hadley cells are massive convection cells in a planet atmosphere. I'm going to use ATM for atmosphere to save some time. So if you guys want to draw the picture of how it should work here, if the sunlight is striking the equator, so first what we're going to do is we're going to imagine that a planet's axis tilt is perpendicular to the ecliptic, okay? That means it's kind of spinning or not spinning, as the case may be, perpendicular to the direction of sunlight. This creates a big column of warm air, which rises north and south, and it displaces a massive column of cold air, which then travels along the surface back towards the equator. And this is what Hadley cells are. On Venus, which has no rotation, you get one Hadley cell per hemisphere. Sorry, my spelling, my handwriting, all of it. One Hadley cell per hemisphere. In other words, the circulation on Venus looks pretty much like this. Guys, because we're talking about an entire planet's surface, a giant massive Hadley cell on Venus, one of them, is so effective at mixing the temperature of the planet that on Venus, the temperature of the planet, 470 degrees Celsius, is the same on the equator as it is at the North Pole of Venus. Think about how weird that is, right? If you go to the North Pole on Earth, it's really cold compared to the equator. But on Venus, one Hadley cell is so effective at just regulating the temperature that the planet has the same temperature no matter where you go. That's, of course, bad for any water that would have tried to exist on Venus in the past, right? Having one giant Hadley cell. The reason why this does not happen on Earth is because of Earth's rotation. Earth actually splits its circulation up into a set of triple Hadley cells, which are kind of like little mini refrigeration units. I know, Matt. Let's talk about it. First, let's write that down. So Earth famously does not have one Hadley cell. It has 3 Hadley cells per hemisphere. It's going to turn out, Matt, that this is one of the reasons why Earth has been able to maintain long-term climate stability. So when I saw Matt's furrowed brows, the question he's wondering is why? Why does Earth split it up into triple Hadley cells? They call these triple Hadley cells, by the way. This is due to an effect of physics that you may not have heard about before. It's called the Coriolis force, or the Coriolis effect. And the Coriolis force is a twisting force that causes a deflection in the movement of atmosphere because you're in a rotating coordinate system. I'm going to explain this better in a second. So let's just say that it's a twisting force caused by a rotating coordinate system. In other words, to use simpler logic, the rotation of Earth splits the atmosphere into triple Hadley cells. I'm going to give a second for you to catch up to the notes, and then I'm going to explain that better. Andrew, let me know when you're done. Andy, where's the camper? Andrew, you're in your car today. Andrew Larson, how you doing?
I'm all done.
Okay. I think it's worth taking a second to explain this Coriolis force because it is understandable with a simple analogy. I want to show you guys a picture of a record player. Okay, so you know they're kind of buried under my junk over there, but I've got a record player and I listen to some records because I'm an old school nerd like that. And you guys, if you are record collectors, you might know that records spin at a constant rate of 33 rotations per minute. At least a standard LP does. A record is an example of what we would call a rigid body rotor. A rigid body rotor, like the Earth, is one in which all parts complete a rotation at the same time. For instance, all parts of the record are rotating around 33 times per minute. Now, let me explain why that's important. One year, there was a lot of ladybugs that surged around the city, and they came into my apartment, and they got all over my record player. And there were ladybugs that were sort of close to the middle of the record player. So here's a ladybug. And then there were ladybugs that landed in the middle of my records. And then there were ladybugs that rotated on the outside of the record. And I watched them go spinning around and around at 33 rotations per minute. Now, let's imagine that there are 3 ladybugs, and I'm going to give them some names here for a second. This is going to be ladybug A on the inside. This is going to be ladybug B in the middle, and this is ladybug C over here on the outside. These ladybugs are kind of like runners on a racetrack, but you guys know that in a real race, the inside runner has an advantage because they have less track to run. But here, all the ladybugs need to tie and win the race at the same time. That must mean that the 3 ladybugs have a different velocity through space, because ladybug C has to complete a giant 12-inch circumference, right? At the same time that ladybug A does inside. That means ladybug A might be moving at, say, 3 meters per second. I'm making these numbers up, but so what? The ladybug in the middle might be traveling at 5 meters per second. And the lady on the outside might be traveling at 5 meters per second. Do those numbers make sense? Does it make sense to you guys why the outside ladybug should be traveling faster? They have to travel a bigger circumference in the same interval of time, 1/33 of a minute. Okay. Imagine what would happen if we had a weird ladybug, a blue ladybug, and let's imagine that the blue ladybug suddenly tried to walk from the inside of the record to the outside while the record was spinning. At first, the ladybug would be traveling at 3 meters per second. But as she stepped over larger and larger circles, the ladybug would be stepping on parts of the record that were rotating faster than she was. Right? The net result would be that the ladybug would experience a deflecting force where she trailed behind the record because the record was moving faster and faster than her. She would experience a twisting force that would go up and to the right. Okay, now you guys try it. Let's say there's a green ladybug. And the green ladybug starts on the outside of the record player. And the green ladybug tries to walk from the outside to the inside. Will the green ladybug feel a deflecting force to the right or a deflecting force to the left due to the Coriolis effect? This is right, and this is left. Can anyone answer that? Will the green ladybug deflect up and to the right or up and to the left as she walks from the outer edge to the inner edge?
To the right.
Jake, walk us through that one. You are correct. Why is it to the right? Use the velocities here. Use the velocities to explain.
She's starting at a faster velocity and moving to a slower one.
Yes. So, yes, that's correct. So why does that mean that she ends up going to the right? Because she's traveling faster than the bits of record over which she's stepping. So she's going to get ahead of the radius arm here, right? She's traveling at 7, but she's traveling up towards the center. So she's going to be going faster than bits of record. And by the way, you can experience this twisting force. If you go over to Roger Williams and go on the merry-go-round, and you take a little ping pong ball or something, and you just roll that little ping pong ball from the inside to the outside, you'll see it do a Coriolis twist. You want to know what else is a rigid body rotor? The Earth. And it turns out that if you travel from the equator up towards the poles, you can experience a twisting and deflecting force. Apparently, for military history enthusiasts, this was a major point, a turning point in the naval battles of World War I, when the British destroyers were trying to sink these German U-boats. They were missing the U-boats for a long time because they were firing over such a long range of latitudes that they forgot to take into the Coriolis effect the twisting of their shells, and they were missing the U-boats. And somebody figured this out, and they made the Coriolis force corrections, and then they started sinking the U-boats, and that became a turning point in the naval battles of World War I. So this Coriolis thing, it's an important thing to know about. It's not intuitive. It's not obvious. You got to kind of learn about it from someone. Imagine what would happen if you were some Hadley cells trying to move across Earth's surface. If some warm weather heats up the air above the equator, if that air starts to move north on a giant Hadley cell, the twisting effect is going to kind of cut it in half and split it up. And it splits Earth into these triple Hadley cells. And let's think about why these are great. This is like Goldilocks in the 3 atmospheres. This is why we have different climates on Earth. You have an equatorial zone. This is called, they have names for each of these cells. I think this is the Hadley cell, this is the Ferrel cell, and this is the polar cell. This ensures that there's always a wide variety of temperature discrepancies on Earth. We have a kind of warm tropical climate. We have these mid-temperate zones where we live in Rhode Island. And then we have these polar regions where the Inuits and the Eskimos live, right? And that means that if Earth suddenly goes through a climate shift where it gets a little warmer or a little colder, there's always going to be kind of a region on Earth that maintains some liquid water. If you melt the ice caps, you've still got some temperate zones where you can have liquid water. If you go into a global iceberg Earth phase, you're still going to have some warmer regions by the equator that have a hard time freezing over. They're like 3 little mini refrigeration air conditioning units. That helps us maintain climate stability. Oh, by the way, liquid water helps you maintain climate stability. And that's because of something called the CO2 cycle. By the way, let me ask a question. We have 1, 2, 3 Hadley cells per hemisphere, right? Now, anyone can answer this, but what do you think would happen if Earth rotated even faster? Like, instead of 24 hours, what if it rotated in like 10 hours or 11 hours? Like the planet Jupiter does.
You'd probably have more Hadley cells to make up for it.
Oh, you mean, hold on. Come on, get out of here. You mean like this?
Yes.
Yeah.
Exactly.
That kind of explains some things, doesn't it, Jake? About why we see these banded cloud tops in Jupiter's. Jupiter rotates in 11 hours. And so what you're seeing when you look at those stripy bands of Jupiter, you're seeing that instead of triple Hadley cells, it has like 1, 2, 3, 4, 5, 6 per hemisphere. It has double. All of these are little circulation Hadley cells. That's why Jupiter has these stripy appearances to its cloud tops. You're seeing the super, super fast rotation break it up into these different temperature zones. By the way, when we look at Jupiter in infrared light with an infrared telescope, these cloud levels actually sit at slightly different elevations in the atmosphere. Here's a picture of an infrared camera image compared to a visible image of the cloud bands on Jupiter. You'll notice that the infrared images show warmer and cooler regions. Notice the connection here between the red clouds in the warm regions and the yellowish white clouds in the colder regions. You can actually see that the yellow clouds are sitting up on top of the red clouds. Isn't that cool? They're mixing a little bit, but they're sitting at different layers. Those are all Hadley cells. Okay, kind of a cool tie-in with where we're going here with Jupiter, right? That's why studying atmospheres is so important. Let's talk about some things that make Earth special. Earth has got a combination of liquid water, fast rotation, protective magnetic fields. And one of the things that has kept Earth's climate so stable is, so I wanted to talk a little bit about the water cycle, but I'm worried I'll run out of time. Let's talk about the CO2 cycle. The CO2 cycle is planet Earth's gift to us. It's a whole set of geological steps that keep carbon dioxide, dangerous carbon dioxide, out of our atmosphere. But remember, carbon dioxide isn't all bad. Earth's global temperature would be negative 15 degrees without the greenhouse effect. So the greenhouse effect in small quantities is actually good for Earth. We're going to take these as notes, but let's just look at the cartoon first because that always makes a big impression. There are several steps. We have volcanism, releasing CO2 and water into the atmosphere. CO2 then dissolves in little rain droplets. Just like in a polar seltzer can, you can dissolve carbon dioxide into water, okay? The carbonated water, which is slightly acidic, then rains down on the continents, which are made of silicate rock. You wash silicate rock into the oceans, you form carbonate rock in the form of limestone and coral reefs and things. That traps the CO2 on the ocean floor. And then plate tectonics slowly pushes the ocean floor into subduction zones where the CO2 comes out again. It's a beautiful little machine here. Let's try to take a note about that because those are things that we'd like to remember. That's kind of a big idea. Okay, so the CO2 cycle is what's responsible for Earth's climate stability. All right?
Yeah, thanks. Oh, it's much better.
Okay. Step one, volcanism. It releases CO2 and H2O, as Andrew pointed out to us early. Remember that I was going to make a point, and I'm missing it here. Because of Earth's global temperatures, the H2O will either condense sort of into oceans, or it can form things like rain droplets and other types of precipitation. It also forms some vapor and some clouds as well. In step two, the CO2 dissolves in rain droplets and other forms of clouds. I don't know if you guys remember this, but there's a reason why Coca-Cola tastes so good when it's fresh and it's carbonated, and it tastes so bad once the soda goes flat. You guys know that brown bubbly Coca-Cola is a combination of H2O. They dissolve some carbon dioxide into the water, and then they add some sugar in the form of high fructose corn syrup. What you might not realize is that the CO2 plus the sugar and the water, they combine to make a powerful acid. An acid which will take the rust off of nails if you leave them in a cup of Coke, or it'll literally dissolve a set of human teeth if they sit in a cup of Coca-Cola for a week. This acid is what gives fresh Coca-Cola its zippy, piquant taste. When the CO2 dissolves out of the water and you get sugar in water, it's kind of gross, right? It doesn't taste fun anymore because you're missing that zippy acid taste. The same thing happens with waters and CO2 on Earth. CO2 dissolves into this rainwater, and when precipitation washes that water down into rock, it can combine with rock to make a form of CO2 enriched rock called carbonate rock. But let's walk through those steps here. So in step three.
Oh, wait. What was HO2 plus CO2 plus sugar? What is that?
That was kind of a sideshow, Andy. It was kind of telling you a relatable anecdote, but it's not necessary for the notes. So I can tell you if you want. It was CO2, H2O, and sugar makes an acid, but it's not necessary. It's just a distraction.
All right.
So rain and other forms of precipitation, they are going to wash CO2 plus water and over silicate rocks. Remember, students, that water can chip away and dissolve silicate rock. That's how the Grand Canyon was formed. And it will wash silicate rock sediment eventually into the ocean as it flows through rivers and tributaries that eventually, fan out into an ocean. Now, in step 4 in the ocean, the water plus the CO2 plus the silicate rock all join together to form the ocean seabed, something that we call carbonate rock. And one classic example of carbonate rock that you might have seen in your everyday lives would be limestone. Let's grab a Google picture of that here. The old New England farmers call it quicklime. I can remember my father trying to treat the scorching of his grass with limestone powder to try to change the acidity because it was killing the grass here. So let's just look up limestone for a second. There are limestone quarries in Lincoln and other places around Rhode Island. I just want to find a picture of this. And I want you guys to notice something here. Whatever. Here's a picture of limestone, kind of this porous rock. What do you guys see embedded in this image here? I don't know if you can see this. This is kind of a lousy picture. Let's find another one here. There's one in particular that I thought was really jazzy. Huh. There were a couple of pictures that used to come up right away. Let me try high resolution. Yeah. I guess that's the one I had a moment ago. Can you guys see little seashells and fossils buried in there? For carbonate rock, I think, is this the picture? About a significant fraction of Earth's carbonate rock, maybe 40%. Oh, there we go. Look right over here down at the bottom. Can you see those little seashell bits and things? I think 40% of the limestone carbonate rock in Earth's seafloor bed is bound up in the shells of sea organisms like coral reefs and seashells and things. A non-trivial percentage of Earth's carbonate rock is contributed to by living organisms. This is one reason why the United States government, when it was sane, went through great lengths to protect coral reefs off the seashore, and different governments around the world protect coral reefs because they are part of the CO2 budget of our planet. And protecting those things is actually important for you to live, weirdly enough. It's hard for the average person to understand that, but they bind up a lot of CO2 there. Do you know that the total concentration of carbonate rock in Earth's seafloor bed is equal to that of Venus's 96% CO2? If Earth lost its oceans and that CO2 rock was exposed to the air, the CO2 would basically dissolve out or sublimate out of that rock in the same way that it does from Coca-Cola if you let it sit on a shelf too long. And that means we have a Venus's worth of CO2 trapped in our ocean floor. Isn't that insane? We could turn ourselves into Venus if we didn't protect that rock. Now let's think about what Earth does with this limestone rock, okay? Oh, sorry, we're taking notes here. View.
Oh, I can't see the rest of them.
Yeah, I'm getting to it here. So now in the ocean floor, we have plate tectonics, which is going to push the seafloor bed into subduction zones. And you guys remember what happens when we push the seafloor carbonate-rich rock into a subduction zone, right? What happens when you push Earth's seafloor crust underneath those continents? Triggers volcanism, says Joel. That's right. And so that triggers volcanism.
Bed.
The volcanism
Shoot.
releases CO2 and H2O and some rock in the form of lava. And then you start the whole thing all over again. Class, how many of the four geological processes are involved in Earth's CO2 cycle? How many of the geological? 3, says Noah. Noah, what are they? Talk to me, buddy.
Rain, plate tectonics, and then volcanism.
Volcanism, plate tectonics, and I write it down is erosion, right? So Earth's triple threat of volcanism, erosion, and plate tectonics are what keep CO2 out of our atmosphere and buried in the seafloor bed. That's great. Now I'm sort of running out of time here, but I'd like to say something. Do you know that one of the best places in the world to do astronomy are the mountains of Hawaii, Mauna Kea in particular? That's where the Keck Twin Binocular Telescope is. And one of the reasons that Hawaii is such an amazing place for astronomy is because it's sort of remote from light pollution, but it's also extremely high up. Here's a picture of the Keck Binocular Telescope, twin 8-meter reflectors, and I'm talking about very big telescopes, right? 8 meters is giant. And there's 2 of them like a pair of eyeballs, and you can see here they sit above the cloud tops. So you never have to have a cloudy day at the Keck telescope. I'm just trying to find another great image. You never have to have a cloudy day at the Keck telescope because you're sitting above the cloud layer. And you're so high up, I think it's like what, 7 kilometers or so, or maybe 8 kilometers. You're so high up that the oxygen concentration is a little lower up there. And from what the professors in my graduate school told me, who would go out there all the time, they'd say, you know, it's a really brutal thing to fly out to Hawaii on an observation mission because usually you're only there for a day or two. You compete for a day or two to use these telescopes. So you select your targets and you write some computer code to point the telescopes. And then you like lose sleep and you fly 8 hours and 10 hours out to Hawaii. You have to stay up all night in oxygen deprived atmosphere. If there's any problem with your computer code, you have to sit there and try to troubleshoot your code while your brain is all stupid and not working well. And then after a night of no sleep, you come down the mountain and then you try to get back on the plane and fly home. It's actually kind of a grueling experience. And that's why you're going to need some coffee to stay awake. And luckily for observers in Hawaii, some of the most delicious coffee on Earth grows on the side of Mauna Kea. That's where the Kona coffee plantation is. Now listen, if you've ever gotten to have some Kona coffee, I remember one of the grad students went to the Keck telescopes and brought me back a fresh bag of this stuff. And I wasn't thinking much of it. I just made a cup of coffee and I thought, oh my God, this tastes so incredible. And I started to realize if you want a bag of Kona coffee, it costs twice as much as other. Now, the part of that is because you're having American labor force. But one of the reasons Kona coffee is so delicious is because it grows on the side of a volcanic island where that fresh volcanic rock has very rich nutrient soil, and it makes for these delicious beans. Of course, at any major university, at any major telescope, they always keep track of the weather conditions for observing with a station that records CO2 concentrations and water vapor. That's because you might have to go back and troubleshoot your data at some point. And I want to show you a cartoon graph from one of my other textbooks in astronomy of the concentration of carbon dioxide as measured above the, hold on a second. My mouse is doing the invisible mouse thing, which I really hate. Okay, hold on a second here. I have a slideshow that's still active. That's what's going on. And I want to show you guys this graph here. This graph is a measurement of carbon dioxide levels for a 30-year span measured at the Mauna Kea Observatory cluster, measuring levels of carbon dioxide in our atmosphere. And from 1960 to 2000, I first want to talk about this little oscillatory cycle. Do you guys see these little oscillations here in CO2 levels? That's due to the changing growing cycle of the Kona coffee plantation, the coffee plants that grow on the side of the mountain. So as you know, plants absorb CO2 and expirate oxygen, right? So when the plants are in bloom, there's a slight decrease in the CO2 concentration as they're absorbing more CO2. And when they're off season, there's a slight rise. That's what nature is doing right there. The cycle of the Kona coffee plantations is causing this mini oscillation. But then superimposed over this, you see do, 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 do. So what do you think is causing that? Not the Kona coffee plants, right? These are man-made contributions to the carbon dioxide levels in our atmosphere. And this is not a political issue. This is a scientific issue. You can measure the concentration of CO2 in our atmosphere. And when you do this, you see changes in CO2 levels. And of course, that goes hand in hand with changes in global temperatures. Although Earth's global temperature has remained roughly constant, yes, there are some years with the hot summers and a cold summer, and they oscillate, but from 1850 to 1900 or so, they oscillated about 15 degrees Celsius. And since then, this was, by the way, this is a little out of date. This was the year 2000. It had gone up by 1 degree. We've since, I think, crossed the 3-degree threshold, which most planetary scientists think could be the point of no return. So CO2 levels in our atmosphere are increasing, and it's worthwhile to take some time to think about what might be causing that. And that definitely has some long-term implications for Earth. Earth does have long-term climate stability. It might have the opportunity to change its temperature over time, but that could take hundreds of millions of years while the Earth goes through a course correction. And if the major coastal cities of the Earth flood during that time, or if we go through some drought periods, that's going to be really uncomfortable for the apex predators of Earth, which are human beings. So it's worth taking some time to think about how we can all contribute to maintaining good CO2 levels on Earth, because we are changing them. Life has terraformed Earth for the good of life so far. Let's hope life doesn't start terraforming Earth in a negative way from here on out. Okay, so I think that's about all the time we have for our lectures for today. So let me go into gallery mode. We're going to take our typical 15-minute pause, and then we're going to do our lenses and telescopes lab. Sound like a plan? Okay, so I'll see you guys, as Chuck Willery would say, in 2 and 2. I'm going to have a snack. Okay, Astronomy 1010. It's time for us to do lab number 7, where we're going to build a simple telescope. This style of telescope is called a Keplerian reflector. Shouldn't take us too long to do it. We're going to be using a pair of lenses, convex lenses. Convex means they've got a belly in the middle and they taper at the edge. And a convex lens is basically just like a magnifying glass, like the kind that Sherlock Holmes would use to investigate a clue, okay? And we're going to use 2 different lenses to build this telescope. One of which is going to be called the objective lens. That'll be the slightly skinnier one. The other is called the eyepiece. That's the slightly thicker one. And I want to give you guys a little lesson about how lenses work. Lenses work by a property called refraction. And for this reason, a telescope built with 2 lenses is often known as a refractor. I'm going to close a couple of my PowerPoints here. I should have done this beforehand. I think that'll just speed up the response time for everything. Okay. Let's see if we can't find a picture demonstrating the law of refraction. Here we go, slide 36. Refraction is the bending of light as it passes through a slab of glass or some other thick medium. Here you can see a ray of light. They've collimated using a slit, a light source into a single beam of light. And when it strikes the interface between air and glass, light travels slightly slower through glass, so it undergoes something called refraction. Refraction is where it bends kind of down and to the right, or towards the normal, as they say. When it exits the glass, it bends again slightly to the left. Refraction is responsible for a whole variety of different optical effects when you pass light through glass. Let's jump up to what I believe is slide 100. Yeah. The law of refraction is often presented in this way in a physics textbook. A ray of light, once it strikes glass, will undergo a bending towards the normal, and the amount of bending is depending upon the type of glass or the medium in which it passes into. And refraction is responsible for a whole bunch of cool optical effects. Like if you've ever seen a stick in water appear broken, or maybe your straw in a glass of water, it's because light that's traveling through the water strikes the interface of air and it bends it or refracts it, and it makes the stick appear broken, even though it's actually one straight line. There's all kinds of fun things you can do with refraction, right? One useful thing you could do is you could design a lens, a piece of glass where you've curved the glass in just the right way. It turns out to be the shape of a parabola. If you shape glass in the form of a parabola, then when light rays from different positions strike the lens, like let's say we were looking at the moon, rays of light that leave the moon and hit our magnifying glass are going to be essentially parallel to one another. And they'll all strike the glass at different angles, and all of the rays will bend to a single focus point. That's where all the light is concentrated in a dot. If you were a little pyromaniac as a kid, like I was, you know that you can take sunlight and you can concentrate it into a single little dot, and you can set the woods on fire behind your house, right? So that's something fun that you can do with a magnifying glass. That little dot where you concentrate all the light in a spot, that's called the focus point of your lens, kind of the whole point. And the distance from the lens to the focus point shown here is called the focal length of your lens. Your first task today is to measure the focal length of two different lenses and then put them together to build a telescope. So let's explain how this works. Most optical instruments use some type of a lens, from a camera right down to your eyeball. Let's cut open your eye. Inside you find that there's this gooey piece of material called a lens, and it's roughly shaped in the form of a parabola. And no kidding, that's what helps you focus light. It all comes to a focus point on the back wall of your eye called the retina. The retina is where light is transformed into an electrochemical signal so that your brain can interpret the images you see. One of the interesting things you're going to discover about lenses is when light comes to a focus point in a lens, it actually inverts the image and flips it upside down. That's pretty interesting because it suggests that everything that you've ever seen in your field of view, you're seeing it upside down. You've just never thought about it as upside down because it's always seemed right side up. Damn, that's heady. Okay, anyways, you'll discover that yourself. If we want to build a telescope, let's just slip ahead a couple of slides here. A telescope consists of not much more than a paper tube and two lenses. One lens is called the objective lens, and that gathers up the starlight. The other lens is called the eyepiece, and that's the one that you stick your eyeball up to, right? But the paper tube is just there to kind of hold the lenses in place. The way things work can be seen in this crappy little cartoon here. Light from a distant source, and if the source is far away, like the sun or the moon, the rays of light will be kind of parallel to one another. They're all going to strike the glass, and they're all going to bend, and they're all going to come to a focus point. Now, if this was a camera, like a photograph camera, that's where the game would stop. And in a photographic camera, you actually put the paper or the picture plane right there. And that's, It turns out that if you put a little card right there at the focus point, a card like this one that I'm going to use today, you'll actually make a little image of the object right on the card. With a telescope, you're not trying to take a picture, you're trying to look through it. So what you do is you remove the card, and the rays of light actually just kind of pass through the focus point, and they travel on their merry way. But now we take a second lens called the eyepiece lens, and we set it up so that the distance from the focus point to the lens is the same as the eyepiece's focal length. You'll notice then the rays of light will come out parallel again. Now this is kind of strange, right? It's like parallel rays come in and parallel rays come out. How does that help our eyeballs? Well, one of the things it does is it makes the image clearer and sharper, and it lets you gather more light. If your eyeball is about this big, right, then your eyeball can only collect maybe 1 or 2 rays of starlight per second from outer space. But if you Campbell's soup condense that starlight here, now your eyeball can collect 1, 2, 3, 4, 5 rays per second. So you're sort of like increasing the surface area of your eye to be the diameter of your objective lens. For this reason, frequently in telescope design, they always have the objective lens larger because it gathers more light. You also want the focal length of the objective to be larger than the focal length of the eyepiece. That's because the greater this length is compared to that length, the more magnification you will have. Because of my somewhat primitive optical system today, our objective and our eyepiece are going to be the same diameter, so it's not going to make a totally awesome telescope. But you will notice in our lab today that the objective focal length must be longer than the eyepiece focal length if your telescope is going to magnify images, okay? What we will discover is that to build our telescope, we need the separation from the objective to the eyepiece to be the sum of the 2 focal lengths. That's important. And at the end of our lab today, what we're going to do is we're going to put these things on a meter stick and we're going to try to separate them by the right length. To do that, I need to measure the focal length of this guy. I need to measure the focal length of that guy, objective and eyepiece. And I'm going to kind of show you how to do it with our setup here. Here, I may want to switch over to phone mode so that you guys can kind of see what's going on. Let's see if my phone will cooperate with me today. Share screen. iPhone. Fingers crossed. Looks good. Yeah. Love it when a plan comes together. Okay. So here you can see my setup. I have this kind of optical bench with some holders, and I've got a light source. It's hard to see, but there's a little cardboard in this light source. A little, let's see if I can, yeah. I've got a little cardboard triangle in that light source we're going to make an image out of. And the name of the game, like here's our objective lens. I can tell because it's a bit skinnier. Just a second here. So here's our objective lens, okay? And what I'm going to do is I'm going to put it in this eyepiece holder. Okay. And what we're going to do is we're going to slide this along to there. And we're going to make a sharply focused image of this cardboard triangle that you guys can see, okay? Sharply focused image of the cardboard triangle. And here I need to kind of write things down and describe what's going on. Okay. We have an optical bench, okay? There's your optical bench. We have a lamp or a light source. And there's a cardboard triangle in front of it. And I'm going to go through great pains to set this cardboard triangle up to 0.0 centimeters, okay? At some position, we'll have a lens, like so. And at some position here, we're going to have a screen. And we're going to slide along the position of the screen and the position of the lens such that the light comes through the lens. And if we put them both at the right position, we should make an inverted and maybe even slightly magnified image of our cardboard triangle. Now, the distance from the object or from the source to the lens, we call that S. That's the source distance. And when it's in focus, the image distance, I, goes from the screen, from the lens, excuse me, to the screen. Our goal is to measure S and to measure I, and then to calculate the focal length using the classic lens maker's formula, which tells us that the focal length of our lens is S times I, source times the image distance, divided by S plus I, source plus the image distance. Okay? So that's our goal. So that's a times up here, and that's a plus. Can you guys write that formula down for me, the lens maker's formula? Okay. So let's get our lab started. Let's see if we can do this right. Up here at the top, as usual, we'll put our name.
Oh, can I see the formula again?
Yeah.
All right. I'm all set.
All right.
Thank you.
This is lab number 7. Please remember to turn this in at the appropriate lab number, okay? You're going to turn this in for lab number 7 today. And of course, it's AS1010, 01, 02, or 101, whatever your pleasure, okay? Let's make a couple of corrections. They say we're going to be using an orange lens and a blue lens. Instead of orange, we're going to have the objective lens. You can just make it OBJ if you want. And instead of the blue lens, we're going to have the eyepiece. EYE, okay? Cross that part out. We're not going to do that. But down here, I'm going to make this objective, OBJ. EYE. You guys got that? All right. So let's start by doing our objective lens, kind of get on with this here. You guys are going to take the measurements with me. So I've got my lens set up. I've got my screen set up. And I don't know if you guys can tell, but that's pretty sharply in focus. Can you see how sharp the cardboard triangle is? Watch when I move it out of focus. Watch what happens here. You see how it gets kind of fuzzy and blurry? And if I move too far on the other side, also gets fuzzy and blurry. There's kind of a sweet spot, which is right about there. It's hard to do this because of the contrast with my phone, but can you see that sharp crispiness? Okay. So a couple of things about S and I. S and I are what we call intervals. Do you guys know what I mean by an interval versus a coordinate? Who could explain what I mean by an interval?
Intervals are separate. Coordinates are just.
Well, like, look at my number line here, right?
Interval would be a certain point.
I'm sorry, say that again?
It would be a certain point.
No, a coordinate is a certain point.
Yeah,
Like-
yeah, sorry. A coordinate's a certain point.
So 60 is a coordinate, right? But an interval is like from 60 to 62, the interval is 2 centimeters, right? So interval is like between two numbers, whereas coordinates are the numbers themselves, right? For S, since one of our coordinates is 0, the coordinate is the interval for S. For instance, what would you guys say the position of this? You've got to measure from the center where that little tick mark is at the 5. What would you guys say the measurement is here in centimeters? Let me stabilize this. What would you say the S coordinate is? To the nearest tenth of a centimeter. You measure, whoa, am I frozen here?
51.6.
No. Oh, yes, sorry. Who said that? Was that Joel? Yes, Joel.
Yeah.
Sorry, 51.6, because that middle line there is at 51.6. So for S, 51.6 minus 0, the interval and the coordinate are the same, right? So let's write that up here. Ah. Now time for our image, okay? We know this one's at 51.6. Let's see if you can, I'm having issues with lighting here. You know what really helped me would be to get a flashlight. Or maybe not. Actually, maybe you guys can read that. What would you say the measurement is there?
$83.8.
Yeah, I'll go along with that. And that means that here's how we're going to do this. 83.8 is the coordinate from 0, but I is the distance between these two. So we have to subtract 83.8 minus 51.6. So 83.8 minus 51.6 is 32.2. Did that make sense, what I just did there? Yeah?
Yeah.
Now we're going to calculate the lens maker's formula, or the focal length using that lens maker's formula. So I'm going to do this really quick. Watch how I do it. 32.2 times 51.6 divided by, open parentheses, 32.2 plus 51.6, close parentheses, equals. Y'all getting that? How many sig figs should we keep?
3.
Yeah. So our final answer?
19.8.
All right. All right. Now we're going to do 2 more trials. And all we do for a trial is we kind of just move this a little bit till it's out of focus, and then we refocus the lens. I'm just going to be sliding this thing forward. Obviously, it would be way cooler if you guys were doing it yourself in a lab, but, you know, COVID-19, making our lives awesome every day. All right. Let's get our S coordinate together. So that you guys can participate a bit, why don't you help me read this once it focuses?
$58.9.
And then we have to get the coordinate here. Uh,
89.9.
You know what? That's a little dark. Hold on. I don't think 0.9 because you have to go from the 5. Let me see if I can find a flashlight, students.
Oh, then maybe it's 0.8. Yeah, it's 0.8.
Yeah, hold on.
Well, it's the center. It's the center of that.
Hey guys, I'm looking for a flashlight because it's kind of dark. Check this out. Speaking of saving the planet, I've got one of those hand crank jobbies. All right. So sorry. Let's try that again. What do you guys think? I heard you guys mumbling when I walked away. What was the consensus?
89.8.
No.
Come on.
You have to read it from the 5,
Oh.
right? Do you see how this? Okay, so there's something that might not be obvious here. The lens is in the center of the holder, and the center of the holder corresponds. You see how there's a 0 and a 10? The reference mark that we should be using is the number 5. So it looks to me, do you see what I'm saying?
$89.4.
Yeah, that's what I think. So let's do that together then. 89.4 minus, what was our other guy?
58.9.
30.5. Can you guys calculate the focal length for me? Oh, don't forget to use parentheses or this isn't going to work. Open parentheses, 58.9 plus. What you get?
$20.1.
$20.1. Nice. Let's do one more trial here. I'll move it back even more. Once again, bring it to a sharp and crispy focus, which is kind of difficult to see without me blocking the light. Right? All right. Give me a reading.
60.6.
I think it's
0.7 rather.
Yeah, 60.7 is what I would say. And okay, this is dark, so I might need the tape. This is all very difficult to do with your phone, but I need to.
0.7.
What'd you say? 90.7?
Yeah.
All right, this is kind of a janky setup here today. You know what it is, guys? It's really dark. Is that 90.7 or 90.8?
That's what it is in my room too. It's really dark.
Can you try to zoom in, Brendan? Will
The
zooming
problem
in
is
work?
my phone sucks for zooming because it's, oh. 90.8, right? Well, it's on the edge, but let's go with 90.8. Everyone cool with that? It's close either way.
Yep.
So 90.8 minus 60.7 is 30.1. And let's calculate our focal length. I get 20.1 again. Let's take the average of those three. 19.8, 20.1, 20.1. equals, then divide by 3. 20.0. Right?
Could you just show the whole table quick?
Yeah.
Thank you.
Is that clear enough? I could go horizontal here.
Perfect.
Brendan,
Yeah. Talk to me.
I'm a little lost on like the last step, like the F in centimeters. What equation are you using to find?
The focal length is found using the lens maker's formula. I just do it really fast is the problem.
Oh, okay. Thank you.
Source
That's all.
times image over source plus image. Do you have that written down, Noah?
I'm about to.
Okay. You must have just got up for a second when I said that, probably.
Got it. Thank you.
You got it. Okay. Let's swap out for the eyepiece. Let's see if we can do this here. Okay. The eyepiece is going to make the image a lot smaller. And that's because the eyepiece has a shorter focal length. To compensate, you're going to see me bring the eyepiece in a lot closer to the source. And now, let me see if I can adjust the heights of these things. A little bit of fiddling and diddling is necessary here. Let me see if I can put you guys in such a way where you can see my fiddles. I really, okay. I'm going to try to adjust the height. Ooh. Unfortunately, the contrast is such that you're going to have a hard time seeing this. What about from the back side? It looks a lot cooler in person than it does on my phone. I think this is one of the things that makes this lab a little bit jankier is the contrast is very harsh on my phone. I think if my phone is an older iPhone 5, so it's not, my camera isn't quite as sophisticated as some of yours might be. I'm going to just fiddle for a second because that's the kind of thing that I do. Bit of a fiddler. And I'm going to try to get it a little further away and make a sharp, crisp image. Let's see if I can get you guys to see that. Okay, here we go. There we go. All right, let's just get the numbers. Would one of you be so kind?
36.5.
Okay. And now this is the coordinate. This flashlight sucks. Now I know why people use ones with batteries. Hold on, I have a better flashlight. Why don't I just set this up and have you guys stare at it? Actually, the zoom feature does work, Joel.
$51.4.
Okay.
Yeah.
So we have to do 50.
No. What?
Hey,
All right.
Andy, I'm going to mute you for a sec. All right. 51.4 minus 36.
14.9.
You guys want to Noah, calculate that focal length. I'll let you guys do that one.
I don't have the number.
Yeah, they are.
I'm gonna say 37.
No,
I got 10.6.
that sounds better.
I concur.
That's what I.
Andrew, watch me do it. 36.5 times 14.9 divided by open parentheses 36.5 plus 14.9. Close parentheses, then equals. You got to use the parentheses. All right, let's move to a new position here. I probably could have used a dimmer light bulb. All right. Sharply focused image, lens.
$39.6.
Yeah, okay. Actually, there's that little focus part. I think it's 39.7. You want to read
Okay.
that? It's close, but
Yeah.
39.7 seems just a wee bit better, right? Well, actually, you know what?
It's right in
No.
the middle.
Yeah, okay. So let's go with it's a judgment call. It's just 39.6.
All right.
Who knows? Maybe it'll come out better. How about for this guy? $54.7?
Yeah. Looks good.
So 54.7 minus 15.1.
15.1.
Time for 15.1. Sorry. 39.6 times 15.1 divided by 39.6 plus 15.1. 10.9. And one last maneuver. Try to move this one a little closer. 10.9 is, all right, yeah. There we go. Oh, sorry, my phone, it really struggles.
And then just tap on the screen. It should bring it into focus.
If this was an iPhone 6, maybe.
I'm gonna say 33.2.
This phone is just, whatever algorithm they use is stupid.
Time to upgrade.
Yeah, I know. It's, you know what the problem is? This phone has just worked for so long that I didn't feel like paying $700 for a new one or whatever the shit they cost these days. They're so crazy. All right. 33.2. I'm going with it. Well,
49.1.
yeah.
Blurry,
So 49.1 minus 33.2, 15.9. Okay, calculate that focal length. $10.8. Now we got to take the average of these three, add them up, divide by 3. $10.8. My battery's holding. Okay. So now we're going to try a slightly different tack. Let me unplug this light source here. We're going to try a totally different method. Hold on a second. I got to clean off my table here. We're going to attempt a new procedure here. When we use the lens maker's formula, this is something called, this is what we use when the source of light is a nearby source. And a nearby source is one in which the source and the lens are close to each other, okay? If we let the source go to infinity, so what I'm going to do in the next section, I'm going to attempt to look out my window and use the source as the street scene that you can see out of my window. And something very interesting happens if we try to play this game when we let the source go to infinity. Let me use the tape to kind of hold my phone here. If I substitute in infinity to the lens maker's formula, now, obviously the street scene that you see is not actually at infinity. But if you were to measure the distance to those buildings in centimeters, they are so many tens of thousands of centimeters away that they are almost like infinitely greater than the 20 or the 10 centimeters that we have for our focal lengths. So let's say we approximate the distance as infinity. Infinity plus, oh, sorry. You can actually work with infinities. If you have infinity times I and you divide by infinity plus I, infinity, like 10,000 plus 10, is still pretty close to 10,000. So this infinity plus I is still infinity. But you have to be careful with times. That's different. If you have infinity times I over infinity, the infinities actually cancel out, and you get that the focal length is approximately equal to the image distance. And this actually means something that's kind of cool here. I want you to watch as I move my rail over to the table. This is a different way of measuring the focal length, and I like to call it the infinity method. I'm hoping this, I'm going to go back to the objective focal length. And here I'm going to try to, sorry guys, I'm having a bad hand-eye coordination day here. I'm going to try to turn my laptop sideways so that you guys can hear me better, because the speaker is kind of unidirectional, and so you can kind of see what I'm doing as I'm fiddling around. I know it sucks watching through my shaky phone here. Can you guys, so this is my setup, and I want to twist it so that you can see me. Can you guys hear me okay if I'm standing over here?
Yeah.
Let's see if we can make an image that you can see on this screen. Ooh, it's really dark. You kind of have to, I've got to close these blinds down and let in as little ambient light as possible. Kind of do this. This works much better on a bright sunny day. So it's, oh, wow. Okay, actually, never mind. All right, so let me see if I can focus this here. Can you guys see that street scene out there? It's actually kind of cool. On a bright sunny day, you can actually see it in focus. But can you see that upside down image of the buildings? Let me see.
Yeah, kind of.
It's too bad my phone is of such a crappy quality. What you're seeing right there is, do you guys know the West End Tower downtown? That's the big West End Tower seen upside down. This is basically how a camera obscura works. A camera obscura will have like a lens or a pinhole, and you put a big sheet on the other side, and you can make like a beautiful cityscape. It's classic technique, camera obscura, in art photography. Very cool stuff. All we have to do this time is measure the image distance. So let me grab my paper, and we'll just do this a couple of times for the eyepiece and the objective, because this is not working today as well as I would have hoped. There is no source distance. The source is at infinity. So we're just going to measure the image distance for the objective and the image distance for the eyepiece. This is the objective lens here. So what does it look like?
Can I see that again? The paper.
Yeah.
What is it?
We're not doing this section, okay?
All right.
This is the infinity method.
So
Well,
OBJ and I.
Huh?
So it's OBJ and I.
Yeah, OBJ for objective, EYE for eyepiece.
All right, I got it. Thank
This
you.
is the objective lens. So let's go ahead and let's just measure our two coordinates. So we have to just subtract this guy minus this guy. Let's do the big one first. Oh man, this is hard to get at with my phone. That looks like 62.5, correct?
Yep.
Minus 51.4. It's a little dark for my calculator. Can you guys subtract 62.5 minus 51.4? What do you get?
11.1.
11?
Wait, what were the numbers?
62.5. Is that the, hold on. Guys, that was the bloody eyepiece. I'm sorry, I meant to swap them out. That's the eyepiece, that's fine. You got 11.1?
Yeah, that's what I got.
Fine. Let's try it one more time. Let's see if I can make a better image. It's actually a little bit better if I bring it closer. I was trying to make it brighter so that you guys could see what was going on here. I need to do some fiddling. I've never done this on such a rainy day before, so it's really dark out there today, guys, if you've noticed. All right, let's just do 2 each because this is getting stupid. All right, so I've got my thing in focus. Let's subtract these two numbers. 26.3 minus 16.2.
10.1.
10.1?
Yes.
Yeah.
Wow, that's all over the damn place. I was expecting a bit more precision there, you know what I mean? All right, let's just swap it out and do the eyepiece because I'm getting angry with myself. I really could use a little more light from the universe right now. All right. $53.9 minus 34.5.
19.4.
You know, I was expecting these numbers. You know what I think? I think we're having a lot of issues because of how dark it is outside. You see how dark it is? I'm not getting enough light through my little 5-centimeter diameter lens, so it's making it quite dark. I was hoping for a little more agreement between this and this, but let's do one more trial. I'll move it one more time. I'm trying to focus on details on the Weston building, but even in my room, they're very grayed out, so they're not going to look too impressive for you guys. The street scene is too dark. Having the sky there is actually helpful. I'm kind of using the contrast between the sky and the buildings. What do you got there?
-61.3.
Minus 42.1. 61.3.
19.2.
So let's just use this third column today for the average. So for the average of this, we got 19.3 centimeters. And for the average of this, geez, we got probably 10.6, right?
Yeah.
Actually, that's only 0.2 off from here. 19.3 versus 20 is pretty outrageous. For our averages, I trust, guys, because I trust the lens maker's formula, because of our infinity method was a little grayed out today and it was tough to get a good focus on the building, I'm going to say that we trust these numbers. Normally I average them with these, but I trust these today more than I trust those. That's a scientist judgment call there, okay? So we're going to go with 20.0 centimeters and 10.8 centimeters. Now the next goal is to find the sum of the focal lengths. If we add those two together, the sum is 30.8 centimeters, correct? So we should be able to build our refracting telescope by separating these two lenses by 30.8 centimeters. So here's the centimeter side. Bear with my shaky camera techniques here. I'm going to take the eyepiece. I'm going to put it in this holder here. Little clip. And I'm going to clip it right at 20.0 centimeters. So this is now clipped at 20.0 centimeters. How far away should I put the other one? Where should I put the
Wait,
eyepiece?
what was
30.8.
what was the bottom of the paper? I didn't see it.
Jesus. Hold on.
So 30.8.
Jake, you cannot put it at 30.8 because if I put it at 30.8, it's only going to be like 15 centimeters apart. They have to be separated by an interval of 30.8 centimeters.
Oh,
So if I'm at 20, where do I want to be?
50.8.
0.8, right? Okay, now you're with me. Okay, so I've done that. Okay, and we have constructed a telescope. Let's do some peeping and see how well this thing works. There's a street scene. First of all, let me look through it. Make a little adjustment here. Yeah. Well, one of our measurements came out a little buggy because I had to make a big adjustment here. All right. Now it's looking good. Let's see if I can do this here with the camera. You've got to get it just the right distance called the exit people. There we go. You guys see through our telescope there?
upside down.
Yes. Telescopes always invert images. They're seen upside down.
That's cool.
Yeah. Obviously, guys, this would have been a much cooler lab if you could have manipulated the things yourself and looked at the telescope. I know this was like a little bit lame, but we're doing the best we can with the situation we're in. So let's make sure you guys get one good long look at that form, at that sheet there. Do you guys have all that stuff?
Yeah, I got it.
Hold on, I don't get it.
I decided we're not going to do the second page because this kind of turned out to be a bit of a disaster anyways. Well, it wasn't a disaster. It just, it didn't go as smooth as I've done this in the past. I was a little unsmooth today. And I apologize for that.
Now I got it.
Okay, cool. So let me get out of this cell phone mode here. Okay. You guys have that sheet? What lab are you going to turn that into? Lab number what?
Lab 7.
Thank you. Thank you, everyone. Thanks for putting up with me today. Oh, whoa, Noah said you visited the Keck Observatory? What?
Yeah, I went there a few years ago.
You're kidding me. What? Tell me about that.
I didn't even know that it was like a famous observatory. We just went there,
Legendary.
my family and a friend.
And so
yeah.
you had to walk slowly because of the oxygen deprivation?
Right. We were kids, so our parents kept telling us we're not allowed to run around because you'll get lightheaded and faint.
That's hilarious. Ava, take care of yourself, buddy. Thank you very much as well. That's so cool. I'm a little jelly. Did you get to look through any telescopes while you're up there?
No, we visited it during the day, and it was so high up that like on the drive back down, you couldn't use the brakes because you'd burn them out. You had to like switch into a lower gear and drive down that way.
That's really scary.
Yeah, they said a lot of people have died on that, on
those switchbacks, right?
On the way down. Yeah.
Oh my God. Oh my God. Yeah, you got to be kind of a competent driver to do that sort of a thing. Hey, Henry. Henry, did you get all that lab? Did you make it through most of that? Okay, cool. All right, guys. Well, that's all for today. Please turn those in right away. Don't forget, okay? And I'll see you guys on Wednesday. Be well.
Peace.